വെൽക്കം സ്റ്റുഡൻസ്. ഇൻ്റെ പ്രീവിയസ് സെക്ഷൻ മൊഡ്യൂൾ 6 ആണ് നമ്മൾ പഠിച്ചുകൊണ്ടിരുന്നത്. മൊഡ്യൂൾ 6 അബൌട്ട് ഗ്യാസ് ടർബൈൻസ് വി സ്റ്റഡീഡ് അബൌട്ട് ടൈപ്സ് ഓഫ് ഗ്യാസ് ടർബൈൻ, ദെൻ വർക്കിംഗ് ഓഫ് ഗ്യാസ് ടർബൈൻ, കമ്പഷൻ ചേംബർ ആൻഡ് ഓൾ. ദെൻ പ്രീവിയസ് സെക്ഷൻ നമ്മൾ ഓൾറെഡി പറഞ്ഞിരുന്നു there are two types, that is constant pressure combustion gas turbine and constant volume gas turbine. Also open cycle gas turbines are there, closed cycle gas turbines are there, also semi closed gas turbines are there. Previous section നമ്മളെല്ലാം അതിൻ്റെ തിയറി ആൻഡ് വർക്കിംഗ് ആണ് പഠിച്ചത്. Then we are going to the TS diagram, PV diagram, that is Joule cycle to Joule diagrams of this constant pressure open cycle gas turbine. So first നമുക്ക് constant pressure combustion gas turbine കൺസിഡർ ചെയ്യാം. അതിനകത്ത് ഫസ്റ്റ് വൺ ഓപ്പൺ സൈക്കിൾ ഗ്യാസ് ടർബൈൻ. ദാറ്റ് ഈസ് ഓപ്പൺ സൈക്കിൾ ഗ്യാസ് ടർബൈൻ. ഞാൻ ഒന്നും കൂടെ പറയാം. ഓപ്പൺ സൈക്കിൾ ഗ്യാസ് ടർബൈൻ, the air is entering in the compressor, the air is compressed, the high temperature, high pressure, the high temperature gas due to the compression is entering to the combustion chamber. It's entering to the combustion chamber. Then we are giving fuel here. Due to that fuel and the high temperature and pressure, it is been burning. Due to that combustion, the high temperature gas is entering to the turbine with high pressure. Due to that, turbine is rotating and there is an exhaust. The exhaust is to the atmosphere. Here it is a TS diagram. As the name implies, it is constant pressure gas turbines. That is, two constant pressure lines are there. P1 and P2 are constant pressure lines. At P1, it is air is entering at the P1 pressure. P1 pressure entry in the air. Compressor compress ആവുകയാണ്. അപ്പോൾ compress ആകുമ്പം obviously there will be increase in pressure, also increase in temperature. അപ്പോൾ ആ 1 എന്ന പോയിന്റിൽ നിന്നും 2 എന്ന പോയിന്റിലോട്ടാണ് ആക്ച്വൽ ഐഡിയൽ കേസിൽ 1 എന്ന പോയിന്റിൽ നിന്നും 2 എന്ന പോയിന്റിലോട്ടാണ് അത് കംപ്രസ് ആവുന്നത്. ബട്ട് ഐഡിയൽ കേസ് നമുക്ക് കൺസിഡർ ചെയ്യാതെ എന്നാൽ when we are considering the actual case, it is compressing from 1 to 2 dash. By considering some losses and all, it is for actual case it is compressing from 1 to 2 dash. In ideal case it is 1 to 2. Then again 2 to 3. Again 2 to 3 we are adding the fuel. That is combustion process. Due to that combustion process, it is taking place in constant pressure P2 and the temperature is increasing from T2 to T3 or T2 dash to T3. In ideal case, the temperature can be increased, can be considered as T2 to T3, and in actual case T2 dash to T3. Then after the combustion process, the hot gas is expanding in the turbine, that is T3 to T4. It is expanding. During the expansion process, there will be a loss of pressure from the pressure P2 to pressure P1, that is 3 to 4. 3 to 4 is the ideal process and 3 to 4 dash is the actual process. Here it is an open cycle. The fourth at point 4, the gas is exhausted to the atmosphere. There is no cycle from 4 to 1. There will be only 3 cycles, 1 to 2, 2 to 3 and 3 to 4 in ideal case, and in actual case 1 to 2 dash, 2 dash to 3 and 3 to 4 dash. Here I explained all the process, that is 1 to 2 ideal isentropic compression, then 2 to 3 is constant pressure heat supply, and 3 to 4. 3 to 4 is ideal isentropic expansion, then 1 to 2 dash is irreversible adiabatic compression, and 3 to 4 dash is irreversible adiabatic expansion. Here we are assuming that the change in kinetic energy between various points are negligible. So we know that inside the combustion chamber itself there will be a change in kinetic energy. We are not considering any kinetic energy change between various points. We have to consider the work output. We know the steady flow energy equation, that is H1 square plus V1 square by 2G plus work input is equal to H2 square plus V2 square by 2G plus heat output, or according to input and output. By applying that steady flow energy equation, we are not considering the kinetic energy changes. Here the work input in the compressor is Cp into T2 dash minus T1. Cp into T2 dash minus T1. Here it is Cp into T2 dash minus T1, that is higher temperature minus lower temperature. That is work input is in compressor, it is Cp into T2 dash minus T1. Heat supplied is Cp into T3 minus T2 dash, and work output is Cp into T3 minus T4 dash. I can show you in the diagram. Here considering the diagram, that is here it is compressor, here it is compressor, and here it is turbine, and here we are applying giving the heat, that is Cp into T2 dash minus T1, higher temperature minus lower temperature. Here T3 minus T2 into Cp. Turbine is Cp into T3 minus T4 dash. These are the three terms here we are explained. Then net work output, we know that net work output is work output minus work input. We are substituting this equation, Cp into T3 minus T4 dash minus Cp into T2 dash minus T1. Then efficiency is net work output divided by heat supplied, that is the thermal efficiency is heat output minus work input divided by heat supplied. This is the thermal efficiency of the open cycle gas turbine. Here we are not considering any of the efficiency improving techniques such as regeneration, cooling, reheating. We are not using any of the techniques. For a simple open cycle gas turbine, this is the thermal efficiency. Then here we have two components, compressor and the turbine. Then compressor isentropic efficiency. Compressor isentropic efficiency is work compressor, we are giving the work in the compressor, that is work input required in isentropic compression divided by actual work required. എത്രയാണോ നമുക്ക് വേണ്ട ആക്ച്വൽ വർക്ക്, അതാണ് നമ്മുടെ ഔട്ട്പുട്ടായിട്ട് ഡിനോമിനേറ്ററിൽ എഴുതുന്നത്. ദെൻ വർക്ക് ഇൻപുട്ട് റിക്വയർഡ് ഇൻ ഐസെൻട്രോപ്പിക് കംപ്രഷൻ. ദെൻ in this diagram, this is the ideal one and this is the actual one, that is Cp into T2 minus T1 divided by Cp into T2 dash minus T1. Cp can be cancelled, then the compressor efficiency is T2 minus T1 by T2 dash minus T1. Here we have to memorize one thing, the actual thing will be in the denominator and ideal in the numerator, but in the turbine it will be opposite to that. That is turbine isentropic efficiency, that is actual work output divided by isentropic work output, Cp into T3 minus T4 dash by Cp into T3 minus T4. Cp can be cancelled, that is turbine efficiency is T3 minus T4 dash by T3 minus T4. There are some methods of improvement of thermal efficiency of open cycle gas turbine. നമ്മൾ ഓൾറെഡി തെർമൽ എഫിഷ്യൻസി ഡിറൈവ് ചെയ്തു. അതിൽ 3 ഇംപ്രൂവിംഗ് ടെക്നിക്സ് ഉണ്ട്, ദാറ്റ് ഈസ് ഇൻ്റർകൂളിംഗ്, റീഹീറ്റിംഗ് ആൻഡ് റീജനറേഷൻ. This is the intercooling diagram, open cycle gas turbine diagram with intercooling. Why we are using intercooling? Because we know that the compressor is utilizing the power or work from the turbine. That is, if we are